Today, authors of a very interesting paper that was published earlier this year in Nature, Ecology, and Evolution. There was a link on the website, the Club EvMed website, for this paper. A really interesting paper with the title, Evolutionary Demographic Models Reveal the Strength of Purifying Selection on Susceptibility Alleles to Late-Onset Diseases. I want to encourage you to take a look at that paper, and we're going to get a nice introduction to it and opportunity to discuss it today. We have the authors of the paper with us, Samuel Pavard, who's associate professor at the National Museum of Natural History in Paris, and his research focuses on the evolution of human sociality and demography, and also the evolution of senescence. And he runs a research team there on human demography. And then we have Christophe Coste, who's a postdoctoral researcher at the Norwegian University of Science and Technology. He got his PhD at the Museum of Natural History in Paris. And his work, his research interests include mathematical ecology, life history, and evolutionary demography. So I'll turn it over to the two of you. Thanks for joining us today.
So many thanks for the invitation. We are very glad to be there and to present this work. So I will share my screen. You will tell me if you can see it.
Looks great.
So I will present this paper that we published this year in Nature, Ecology, and Evolution. And I will start right away because I plan on a presentation that may be a bit long, so maybe I will shorten it along the way. Okay, so the aim of this study starts with basically in the 90s and late 90s, when geneticists thought that looking at the genes of individuals, they could be able to predict their susceptibility to late-onset diseases. And behind this hope, there were a theory called the common disease, common variant theory or hypothesis, which was that to a common disease, such as diabetes, cancer, stroke, heart disease, depression, and asthma, is associated to common variant. And this theory was based on a belief is that late-onset disease occur at age where nobody were surviving in the past, or after menopause. And so late-onset disease were leading to death or incapacitation at age that has no impact on individual reproductive value anymore. So this allele, the alleles coding for this late-onset late-onset disease that we call susceptibility allele to late-onset diseases, were thought to be neutral. And if they are neutral, it means that there is no negative selection purifying these alleles, so purifying them out of the population, and that the fate of this allele were driven only by genetic drift. And we know the effect of genetic drift on the allelic spectrum of a disease. It tends to lower the number of mutations because a lot of them are driven out of the population and go to extinction, but the remaining ones are found at higher frequency. So basically what geneticists were expecting is to find a small amount of mutation at large frequency and explaining a lot of the prevalence of late-onset diseases. And 20 years later, here we are. Here are the 205 couple gene late-onset diseases recorded in the online Mendelian in Main database. And things are much more complicated than what was expected, with genes involved in different diseases. Disease, of course, under the control of different genes, but most of all, most alleles involved in genetic disease, including familial form of cancer, coronary artery disease, and Alzheimer's dementia, are recent and rare. So exactly the opposite of what was expected. And for example, I put here the example of BRCA1, which is genes whose mutation may lead to susceptibility to late onset cancer, breast cancer and ovarian cancer. And the 3/4 of mutations in these genes, we found thousands of mutations, and the 3/4 of them are found at very low frequency and even in only one family. So instead of finding a small amount of mutation at large frequency explaining a lot of the variants of late-onset diseases, we found many, many mutations, each of them explaining really little of the prevalence of common late-onset diseases. So this has led geneticists to propose a new theory, a new hypothesis called the numerous variant common disease hypothesis, and to postulate that the common disease, common variant idea is largely wrong, and that natural selection has been likely more efficient in purifying these alleles out of the population than expected. And you've got on the right here an example of this kind of study. For instance, here you've got the odd ratio of developing the disease for individual carrying mutation, susceptibility mutation to late onset disease. And you can see that common variant seems to be associated with lower risk than a rare variant, leading the author to postulate that a natural selection, negative natural selection, has been selecting against the rare variants. The problem for geneticists on this is that these theories are based on two main papers by two very famous population geneticists, Reich and Pritchard. And in their paper, they discuss at length parametrization of mutation rates, for which we've got good empirical data. They discuss at length mutation frequency, for which we have also now good empirical data, but very little about the magnitude of selection, for which we do not have good empirical data. And one of the problems with selection is that we know how to estimate or to test selection, positive selection from genomic data, but we don't know that much how to estimate it for multigenic disease involved in complex molecular pathway, and in the case of weak negative selection. So up to now, there is no selection test allowing geneticists to estimate the magnitude of negative selection from genomic data. So we start from this, and the aim of this paper is to see what demographers can predict from a demographic model about the magnitude of selection on these susceptibility alleles to late-onset disease. And indeed, there are three main phenomena that can explain why susceptibility alleles to late-onset disease may be under negative selection, although the mean age of onset is late after menopause. The first one is variance is disease onset, and it is the fact that disease may occur in mean before menopause, but a lot of the distribution of the onset may be anyway before menopause. And you have here the example of BRCA1 again, where the mean age at breast or ovarian cancer for women carrying a mutation in BRCA1 is about 56, 58, but still 25% of women develop a cancer before the age of 45. So what we did in this paper is that we review literature on several articles where we have indication on the mean and the variance of the onset of the disease. And we show, for instance, this is in the supplementary materials, but still it's quite interesting, the fact that basically the later is the mean age of onset of the disease, so the more the disease occur in mean at advanced age, the larger the variance. So if the disease is occurring at later mean age of onset, it means that there is anyway a lot of individuals developing the disease at younger ages. So in this article, basically, we first model a large parameter space for the mean and the variance in disease onset in order to explore the parameter space, the realistic parameter space for late-onset diseases in humans. But we also take 22 couple genes disease for which distribution has been estimated. So for which we've got good estimates on the distribution of the age at onset for individuals carrying a mutation in these genes. So you've got, for instance, breast and ovarian or prostate cancer, colorectal cancer, Huntington diseases, late-onset Parkinson diseases, frontotemporal dementia and amyotrophic lateral sclerosis, Alzheimer's disease, and polycystic kidney disease. So I took here the example of polycystic kidney disease. It is a publication in epidemiology where we've got a good estimate. Here it's a survival of the kidneys of the onset of the disease with age, with distribution in mean and in variance. The second phenomenon that I can explain that this susceptibility alleles will be negatively selected is that men can reproduce later than women until old ages. It is often forgotten in population genetics where most of models are one-sex models because they are much easier to parameterize, especially the model for inferring allelic spectrum. But actually they are not one-sex models, but they are models where the two sexes are behaving in the same way, the same demographic parameters. But actually, it's not true. And here you have data for a different population where you've got in red fertility of women and in blue fertility on men, a pre-industrial, non-industrial population. And you can see that men can reproduce up to older ages, even after age 50. So when all women, most women have menopause, and that it is due to different factors, cultural factors. The first one is the difference of age at first birth, which is driven by the difference of age at first marriage. And we'll see that in most populations, men are older than women at the first marriage, but also by other cultural factors like polygyny or remarriage of widowed or divorced men with younger women. So for instance, here I took data on age at first marriage, and you can, so here as the mean age of marriage for female and the difference of age for men, between men and women, and you can see that all the points are positive. So there is no one population for which we've got data where in mean women will be older than men at first marriage. It's always a bias in the opposite sense. And it's the case even in society where sexuality is not prohibited before marriage, and even in matrilineal and matrilocal society for which we could think that woman has more control over their matrimonial and reproductive life. And it's still the case in modern developed population. In France nowadays, there is still 3 years of differences between men and women in weddings. The second factors here, it's widowhood. Widowhood is quite frequent. If you take data in the literature, you can do a simple calculation in calculating the percentage of men who would have lost their wife reaching the age of 50. And it's about 1 man over 5, which get married, but who lost their wife before reaching age 50. So susceptible to remarry with another woman and often a younger one. Divorce is really common, so I'm already late, so I will not say everything, but anthropological literature has shown since a very long time that in many, many populations, divorce is really frequent. It's not something rare across societies, it's something really frequent. And the last factors explaining the possibility for men to marry and reproduce with younger women is polygamy, holding to the fact that polygamy is really frequent. It's found in nearly 73% of society, but in most cases, polygamy is really rare. And it's found at low frequencies within the frequencies. And actually, societies where polygamy is really frequent are quite, not, it's not rare, but it's not the majority of recorded society in anthropological literature. Okay, so in this article, what we did is just that we fit mean fertility for men and women from data. A point that has to be made is that in this paper, we tried, as I will explain, to build up a two-sex population genetics model. So we need children to be born from parents of known age. And to have parents of known age, but we have to model also what we call the union function, so the function that describe couples giving birth to children, and couples with a mother and a father, but of a known age. So it's a bit tricky, but we cannot modelize separately fertility of men and women, and we have to incorporate the fact that their fertility is a product of union between men and women. The third factor that can explain selection on susceptibility allele to late-onset disease is that fathers, mothers, and grandmothers can care for their immature children long after menopause. So it's called parental or grandparental care in the literature. So in this paper, we review 31 studies that have estimated the relative risk of death of orphans from mother, father, and grandmothers compared to non-orphans. So basically, for instance, in the first graph, you've got on the axis the child age at maternal death, and on the ordinate the relative risk of death of children according to their age at the death of the mother. And you can see that in most population, and the vast majority of population upon which we have been measuring this, that a child who has lost his mother has a higher risk of death than a child whose mother is alive. So it's not really a surprise, but please note the magnitude of this risk that we can estimate in means, for instance, at birth, around something like between 10 and 20. So a motherless child at birth will have in mean 10 to 20 more times a risk of death, 10 to 20 times higher than a child whose mother is alive. So it's quite large. For motherless children, but it depends a lot of the population under study, but in mean, we can say that children with mother, grandmother will have higher survival than children without grandmother. Although you can note that the risk is in mean much lower. We are around 1.1, where we are something between 20 and 2 for mothers. Okay. And of course, literature distinguishes between maternal grandmother and paternal grandmother with a small bias towards maternal grandmother, which seems to have most of the time a larger effect, or at least well, it depends on the kinship system. I will not talk about it. A point to be made is that in most populations, it is either the maternal grandmother or the paternal grandmother that have the largest impact, sometimes both, but most of the time it's one or the other. And for the father, results are really contrasted. There is many cases where we don't find any effect of the death of the father on the survival of the child, on the mortality of the children. but still, in mean across population, we can estimate that it has an effect around in between 1 and 2, something like this. So in this population, we take this mean estimate, and we consider that a child survival up to maturity will depend on whether his mother, his father, and his maternal grandmother, we choose the maternal one in this paper, is alive or not. And that these risks are multiplicative. So if your mother, your grandmother, and your father are all dead, you have a much larger mortality risk than if they are all alive. And so what we try to build, it's a model that allows us to estimate coefficient of selection for susceptibility mutation to late-onset diseases, incorporating these three phenomena. So for a large and realistic parameter space for disease onset with mean and variance in disease onset, in a two-sex model where men can reproduce at all ages, and where child survival depends on maternal, paternal, and grandmaternal care. So to do this, we need to calculate the mean number of children of individual carrying or not the mutation. And so we need a population genetics model. And we want to do it where the child survival depends on maternal, paternal, and grandmaternal care. So in order to do this, we need a demographic model in order to calculate this survival. So I will spend really little time on the demographic model, just to say that basically, in order to build up such a model, you have to express the survival probability of a child as a function of the age of the mother at their birth, the age of their father at their birth, and the age that will be the grandmother if she was alive at their birth, in order to calculate the probability that each of them will have to die in the years following the childbirth. So I'm passing fast because I don't have the time. We can discuss about it if you want later on. Just a point, just to notice that in the derivation here, at one point, you need absolutely to have the population growth, the instantaneous population growth for demographers. Demographers know that well. It means that in order to be able to solve this, you need a continuous model of population dynamics, and it is which makes things really complicated, is that to solve this, you cannot stay with a traditional population genetics model with non-overlapping generation. You need generation to overlap. And you need generation to overlap, so you need an age-dependent model. So you need a continuous model of population dynamics. Okay, so but with this model, at one point, we succeed to calculate the reproductive success of male and woman, men and women, non-carrying the mutation, and men and women carrying the mutation. And it's here that it's starting to be a population genetics model, is that if you carry the mutation, but first, there is one chance over two that you are a man or a woman. If you are a man, then, and you are carrying the mutation, we will consider that the mutation is at low frequency, so low that your wife is non-carrying, and that the mother of your wife is not carrying the mutation. So, for instance, in this first part of the equation, the susceptibility allele will increase the mortality of the carrier male, so it will have an effect through paternal care only. But there is also one chance over two that the mutation is carried by a woman, and if it is carried by a woman, we will consider that there is one chance over two that this woman has inherited the mutation from her father, and in that case, her husband and her mother are not carrying the mutation. But there is also one chance over two that she has inherited the mutation from her own mother. So in that case, the mother of the mother, so the grandmother of the child, will carry the mutation. So we'll have an increased mortality due to the morbidity of the disease. So this equation is quite flexible. So you can see that using this equation, we can calculate selection for mutation in various genetic compartment, for example, in autosomus like this one. But if it is a mutation on the mitochondrial chromosome, for instance, you just have to cancel the male part. And if it is a mutation on the Y chromosome, you just have to cancel the female part of the equation. And you can also calculate it for sex-specific pathology, for instance, when in case of BRCA1, for instance, when the cancer will develop mostly in women. So it's quite a flexible equation that allows us to calculate selection for sex-specific pathology or for mutation carried in autosome, in mitochondrial DNA, or in the Y chromosome. So assuming that there is a lot of assumption in the paper, we have to be really honest about it. We assume allele at very low frequency. We assume that the disease is lethal or fully incapacitating individuals at a given age. We assume independence between the risk of onset of a specific disease and other causes of death within the population, that we know that is sometimes not the case. We consider no pleiotropic effect of the allele, and obviously we assume that the epidemiology of the disease, in the part where we are estimating selection coefficient on current pathology, we assume that what we observe now is identical to what could have been observed in the past, that we also know that it is likely not true, for instance, for cancer. The result now that all these caveats and assumptions have been said, so you've got here how to read this graph. So it is the selection coefficient here calculated as a function of the mean age of disease onset on the x-axis. And on the left, it is in the case where there is no variance in disease onset. So disease occur on one specific age, the mean age, not before nor after. And on the right panel, it is the case where you've got variance in disease onset. Here it's modelized through the mean of the first age of onset. So you've got a given mean age of onset, but the first time you see the disease is 20 years younger. So for instance, a disease with mean age of onset at age 60, as the first time you see the disease, it's at age 40. Okay. And you've got a color code. So the blue one is when no social cultural factors are incorporated. The red dark one is when only maternal care is incorporated. The green one, it's when you've got maternal care plus grandmaternal care. The pink one is when you've got maternal care plus grandmaternal care plus male fertility. And the orange one is when you've got maternal care plus grandmaternal care plus male fertility and plus paternal care incorporated in the calculation. So you can see that the blue curve here, it is basically the common variant, common disease hypothesis. So we forget about the variance in disease onset and we forget about any sociocultural factors. And as predicted early 90s, you can see that before menopause, the selection coefficient is dropping down to magnitudes where alleles can be considered as neutral. I forget to say, the very light gray area here, it's the area where you can consider that alleles are neutral in all human population. The dark gray area, it's the area where you can consider that alleles are under negative selection in all human population. And in between, it will depend on the effective size of the population. So here it's more population of small effective size, and here population of more of larger effective size. So basically here it's population that you can think of small effective size like hunter-gatherer, etc., etc. And here it will be more recent large population like the pre-industrial population. Okay. So you can see that in the common variant common disease hypothesis, that the selection coefficient is dropping to 0, but you just have to add variance in the equation to push negative selection to occur up to much older ages. Here up to age 57, here you are quite sure to have negative selection in all human population, just to add variance in disease onset into the equations. Now we can look at the effect of maternal care. Maternal care has quite a large effect for disease with low variance, a smaller one with disease with large variance. It's quite easy to understand is that maternal care in our model has an effect only in the 15 years following the birth of the children. So basically past age 65, women, the care that women are providing to their children are for sure care for children older than age 50, because the last child that she could have had is around 50. So past 65, all her past children are older than 50. So the maternal care in this case is not incorporated in our study because we stop maternal care at age 15. All right. Most interestingly, grand maternal care has here a very large impact on the magnitude of the selection. I was quite surprised because I was not a big believer of the grand maternal care hypothesis before to do this work, just because I thought that, I'm coming back here, the effect of maternal, of grandmother is really small in terms of the child survival. So I thought that compared to maternal care, which has a very strong effect on child survival, grandmother, bon, it increased survival of 1.1. It's not that much. So I thought that we could have expected a much lower effect for grandmother than for mothers. Actually, it's not at all the case. And digging a little bit, it's quite obvious. It's because grandmother has much more grandchildren than mother. So their deaths are impacting much more grandchildren than the death of the mother impact children. And so this is the first effect. And the second one is that grandmother at the range of age where disease occurs. So they are much more susceptible to die from late-onset diseases than a mother. So at the end, these two factors incorporating, grandmother has quite a very large effect in maintaining negative selection and late-onset and susceptibility to late-onset disease until old ages. When you incorporate male fertility, it has a large impact, not that much on old ages. Still, it has an impact here on all ages, but it's much more on the intercept. It has a really strong impact on the magnitude of selection all over the range of age, but as soon as very young age, as 40. You can see here that it's joining the curve of grand maternal care. It has no more effect. It's because when you don't have variance in disease onset, but it's the same as for mother. All the parents past age 70, there is not that much of males reproducing anymore, even in population where men are reproducing at all ages. Past 70s, it starts to be a rare event. But you see that when you've got variants, because a lot of men reproduction still occur in between 50, roughly, and between 50 and 70, you still have large selection, even on susceptibility alleles, leading to mean age of onset around 70 and even 80. Okay, so the conclusion is that when all sociocultural factors and variants are incorporated, you still have a large magnitude of negative selection, even for mean age of onset, about 70, for instance, here. Okay, so I'm going faster on this, and I'm going directly to the result concerning specific disease. So here, these points are estimated for published distribution of disease onset with age. And so you've got here the genes, and here the disease, the genetic disease. And you can see that in this graph, you've got basically two types of disease. On the left side, basically the cancer and Huntington disease, where the magnitude of selection is largely independent on sociocultural factors. So the variance in disease onset is enough for this disease to expect negative selection in all human population. However, on the right part of the graph, you see that for mostly here neurodegenerative disease and polycystic kidney disease, the magnitude of selection will depend, you've got more variance here between the point, will depend on the sociocultural factors that are included into the calculation. So you may expect this disease to show different allelic spectrum according to the magnitude of these sociocultural factors. Typically, for instance, between a population where you have different infertility between males and females, you may expect different magnitude of selection on negative selection on these late-onset susceptibility genes. So to conclude, we show that it is likely that there is a purge of deleterious mutation, even for mutation leading to disease at old ages. And this is due to the physiopathology of the disease, the variants in disease onset that are often not considered into genetic study, both theoretical and empirical, but also from socio-behavioral factors like the matrimonial system or the caring system. A distinction can be done between cancer and Huntington in the right hand that are likely negatively selected in all human population, neurodegenerative disease that may be varying in terms of magnitude of selection according to sociocultural behavior and effective population size. So for instance, we can make the hypothesis that, for instance, neurodegenerative disease has been under negative selection only recently in the past of human population, only when population actually have reached population effective size large enough for negative selection to overcome the effect of genetic drift. And the last point, I didn't talk about it, but we also explore where demographic regimes influence our result, and in fact, they don't influence our results that much, and we are really surprised about it. So basically, our results are quite robust to variation of adult survival into the population. Between population with large adult mortality and low adult mortality, actually doesn't change that much the magnitude of the selection. And that's it. I will be glad to answer questions or comments or critiques or whatever.
Okay, thank you very much. That was great. Samuel, can I ask you to stop the screen sharing so we can see everyone again?
Yeah.
Excellent. Thank you. That was really good. Do we have any questions? Anybody like to ask their questions? There have been a few questions in the chat. Okay, I saw Tom's hand go up. Go ahead, please.
Hi, thanks a lot, Samuel. That was just a really stimulating talk. I was wondering about, so the main results plot you showed with the different curves along with maternal effects, paternal effects, grandmaternal effects, et cetera. One of the cases that you didn't show was if you had maternal effects and paternal effects without the grandmother effects added. And my question is whether or not that still only has an effect on the intercept of those curves, or whether it would also push things to the right, similarly to the way that the grandmother effect does.
No, it has also an effect on the intercept. It's exactly. In fact, I did it in a cumulative manner in order to make it more visual. Otherwise, the curves are just crossing. So just for the graph to be more clear. But if you took into account only maternal and paternal care without maternal grandmothers, you still have the same patterns for selection. It's just a little bit.
Yeah. So that does provide then even stronger evidence that it's really the grandmaternal effects on the large number of grandkids that is pushing those ages much later, where the negative selection.
Yeah, definitely.
That's fantastic. Yeah, awesome. Thank you.
Samuel, your model suggests that we should be able to detect selection on a lot of the genes that you listed, and you had those estimated selection coefficients. I mean, when people actually look, how many of those genes are they able to detect selection on?
Yeah, in fact, the most recent study on this, the most complete one, it's Blackman in 2008. But what they did is that they test whether disease with mean age of onset older than 40 will exhibit different selection than disease with mean age of onset younger than 40. And actually, they don't find any difference. And one of the reasons, maybe, but first, they don't consider variance. So the categorization of their disease may not be right, because you may have a disease with later age of onset and large variance, and disease with young age of onset but with short variance. So maybe it's compensating each other. But the second element of answer may be that actually the selection, what we call the selection gradient, and the decline of selection with age, is much more flat than we were expecting. And if it is flat, but we have more difficulty to contrast young early onset disease to late onset disease. So I think it's not easy to estimate. It's not easy to have a comparative design between diseases. Okay. And now to estimate it for one specific disease, but it was a saying, we don't have tests, to my knowledge, able to estimate weak negative selection. We know how to detect positive selection quite well, but negative selection, it's much harder.
So what do you see as the next major steps, for advancing this area, given the outcomes from your model?
There is two things that we would like to do but it's to add antagonistic pleiotropy, because for several genes, it has been shown, polypoprotein E, BRCA1, etc., which is absent in our modeling. The second one is that we are a little bit constrained here by classic population genetics framework, because it's already complicated from the demographic side. So the genetic side is as simple as possible, but most of these diseases are complex. So to rightfully estimate selection, we should do network of genes. So actually, the examples that I took are quite okay in the paper, because they are mostly dominant genes. But if we want to open the window to more complex disease, we have to do much better in terms of population modeling.
Okay, we had thanks for that. We had a question from Shaquille. It was in the chat box under NS. She asked me to ask you this question. She's unable to ask it at the moment because she's on the road. You can see it partway up around 138. Mirror neurons allow us to learn through imitation and emulation. Could it be that mirror neurons are behind the grandmother effect? I don't know if you have any thoughts about that.
I'm not a neurobiologist.
Yeah.
I'm sorry, it's really out of my field.
Christophe,
I know what mirror neuron does, but to incorporate them in my work,
yeah.
I have
Anybody else have any thoughts to share with Shaquille? And Christophe, I was wondering if you had anything you'd like to add to all of this. Any other responses to the question so far?
No, can you hear me?
Yes, perfect.
Yeah, okay. No, just I think just to reply to this, I know it's not a reply, but just to comment on the last question that you asked. I think basically the grandmother hypothesis, in a way, it's not really an hypothesis when you put it into the model. It's just you just implement something very simple, and we've got numbers for it, which is the effect of grandmothers being alive or dead on survival. And because we have a demographic model where everything is structured by age, then it's not magic, it's mathematics, but like it's incorporated, and then it's part of it, and then you can see it in selection gradients by age at the end. So it's just something very simple, which is just in what societies do grandmothers have an impact on the survival of offspring, and in which societies does that mean the selection is also strong at older ages than we thought before. Yeah.
Okay.
And yeah, just one comment from me on the modeling side is that it's actually quite complex in this paper already, even though it doesn't really look that much in the paper itself, but it's because you've got two sexes, which is not really something very common to, even from a evolutionary demography perspective, most models are one sex. So having mixing population genetics, two sex, age structured demography, yeah, so we can add more stuff, as I heard Samuel say about like antagonist pleiotropy, but it's getting, then you need to make sure you can run those models with like acceptable computation time.
Well, I have to say, I thought the paper was really clear, and it was, there is obviously a lot of complexity there, and that came through, but you did a really good job of describing it. And then Samuel, you did a fantastic job of leading us through each of these different aspects and walking us through that plot. So I'm really impressed with your ability to basically identify these three areas to model, and then to implement that and be able to explain it. And obviously there are more things that could be done.
In fact, it was a bit the challenge of this paper. It was the writing, because I'm not an epidemiological geneticist. I'm not a medical doctor either. And it was a challenge to write the paper to reach people outside our field, to be able to talk to real geneticists doing association studies or stuff like this. And we put a lot of effort in trying to reach this audience, which is not ours, basically.
Yeah, I thought you did a great job. It's really good. We have another question in the chat from Shiobon Madison. And you can see it in there at 146. She wrote, are there any translational insights from these results? E.g. the extent to which genetic variants, genetic versus other targets can lower incidence and or morbidity. I wonder if you have any thoughts about that, either of you.
Can you repeat the comment?
Yeah, it's in the chat at 146. Are there any translational insights?
France? I don't see the chat at
Are there?
transnation. national, right?
Translational insights.
I'm not sure. I
So
understand.
yeah, maybe that's kind of an American term. You know, how does this apply to actually clinical practice or medicine, improving health? That's how I would take it.
Actually, how to answer to this? Actually, what we would like to do now, it's two things. It's really theoretical. Again, I don't know if we will go up to practical application of this, but what we would like to do is to test, for instance, whether different populations differing in their matrimonial system exhibit different allelic spectrum for given old age diseases. I think, but I may be wrong, that the difference between male and woman fertility are the most easy to detect cultural things between population. And so I think we could contrast population according to their effective size on the one hand, and their difference in men and women reproduction on the other hand, and to see if at the crossroad of these two parameters, we can find a different allelic spectrum of all ages diseases, and especially contrasting cancers and neurodegenerative disease. If it leads to results, here it starts to have an epidemiological insight which is not completely out of medical application, because you could predict, for instance, the prevalence of a population aging disease, neurodegenerative or cancer, according to some simple covariates like men and female fecundity and population effective size. So this could be an application.
Okay.
I don't know if it's answering the question. Sorry.
So population health, public health.
Yeah. Of course, the aim of the study is to understand the allelic spectrum. So population factors. We are not at the individual level here.
Okay, we're at the top of the hour. I want to thank you, Samuel and Christophe, again for a really great presentation. And thanks so much to everyone for tuning in. It's great to see you. We're going to be back again in 2 weeks, if I have it right. We have Paul Turner coming up next from Yale. We'll have a title up on the website pretty soon and share that with everyone. And just really great to see you guys, and great to hear this talk and to have a deeper understanding of this paper and the really interesting results. So thanks very much, everyone. Hope to see you at our next one in a couple weeks.
Thank you.